So let's talk about trigonometry. And trigonometry has to do with, angles and finding the various trigonometric functions of those angles and a whole host of other things. It's a lot of triangles and circles. But I think kind of the place where it makes the most sense to start is how we measure angles. And there's actually more than two, but there are two systems of measuring angles that we are going to use and that most people in the world use. And that is a system of either degrees or of radians. So, and also I should back up a little bit. I'm going to start very from a basic, assuming everyone has kind of the same base level of knowledge, which is not very much. You'll probably know some of the things I'm already saying. That's okay. It's good to hear things again. But if you feel like I'm going slow, I'm sorry if you feel like I'm going slow, but I want to make sure that everyone kind of gets to see the full picture. And don't worry, we will eventually probably pick up pace. Also, I need to open the chat because I keep forgetting about it. So I don't think you need to sketch this out. I'm certainly going to, so you should take whatever notes you think you want to take. Yeah, that's a fair question. I will definitely upload a PDF of the notes after class, so you can certainly look at them again. So if you don't get this written down, it'll be there later for you to look at. Welcome to whoever just came in. Oops. The one thing about this room is that if you don't move around enough, the lights go off. And usually there's plenty of students in here to make that happen, but then I have to go do this to make the lights come back on. And sometimes you wait too long, you have to walk all the way over and turn it back on. Which seems kind of silly. But that's the way it is. So yes, welcome to whoever came in just now. So the thing I want you to take away from this picture really is that this length here is the radius of this semicircle or circle, but right, it's half a circle. So all these lengths are the radius. And what makes a radian, this angle here, that's 1 radian. It's 1 radian because this arc length is exactly 1 radius long. So this length here and this length here are the same. And so when someone says something is an angle measure of 1 radian, it just means that whatever this angle is corresponds to the length on the circle, the arc length being 1 radius length worth. But usually we don't really remember that. We're like, okay, there's 1 radian. And in half a circle, or in a semicircle, there's a little more than 3 radians worth, right? There's 1 radian, there's another radian. And again, a radian is an angle. There's another radian, and then there's a little tiny bit more. Well, how much is this? It's actually exactly pi radians. And the way I think about it is, well, here's how I really think about it. I'll come back to this picture in a second, but what I really think about when I'm thinking of this is that a circle with a radius of r, the circumference is equal to 2 pi times the radius. So that means if you go a full 360 degrees, well, the arc length around that is exactly 2 pi radii, right? If you go the full circumference of the circle, that is 2 pi times the radius, which means the angle is a full 2 pi radians. So 1 full circle has an angle of 2 pi radians, which is equal to 360 degrees. Or, more easily seen, half a circle has 1 pi radian. Radians, really, right? Pi is a plural, it's pi radians. So this angle here is pi radians because this arc length up here, it has a length of pi times the radius. And then the important thing to remember is that that's equal to 180 degrees. So I know it's written right here, but I want to really kind of make sure you guys see that. Pi radians is equal to 180 degrees. We're going to use that a lot. Also, I will certainly stop for questions sometimes, but if you ever have a question, you can write something in the chat, or if you want, there's also like a way to raise your hand on Zoom. Everyone should do that. Everyone raise your hand right now on Zoom, like with the little button, just so you can see how to do it. Awesome, great. And then I think you also do have to lower it yourself, right? So if you don't lower it, it'll stay there. Cool. Everyone knows how to do it. Great. If you don't know how to do it, you can practice with me later in office hours. Okay, so pi radians angle measure is the same as 180 degrees. And you might wonder why I emphasize that so much. I mean, other than we use it all the time. I remember myself kind of not having a great idea of what a radian was. But just to look one more time, 1 radian is that angle there. It's approximately 57 degrees. I usually think of it as being pretty close to 60 degrees because 60 degrees is a pretty common angle that we deal with. And yeah, I don't really need this picture anymore. My circle is not so big. So we have the following. 180 degrees is equal to pi radians. Now, something important to know is that we don't usually write radians. We usually just say pi. So really, we just say 180 degrees equals pi. And everyone knows you mean radians. When you're talking about degrees, you always have to write this little symbol, that little circle in the upper superscript there. When you're talking about radians, radians are called a dimensionless unit. And the reason they don't have a dimension is because you end up dividing a length by another length. So if you had like 12 feet divided by 2 feet, you'd have 6 radians. So when you don't have any units, it kind of gets weird. But we've decided, okay, we're going to call these things radians. And yeah, there's no feet, there's no inches, there's no degree symbol. They're just are what they are. So if someone says they have an angle, you have to be careful. Because if they don't write this little symbol, it means it's radians. And if they do write this symbol, it means it's degrees. And people get lazy sometimes. So definitely, I would encourage you all to be very kind of rigid when it comes to mathematical notation. You definitely want to be like, oh yeah, that angle has degrees, I need to write degrees, or that angle doesn't, I don't write degrees. So here's how we convert. So we want to convert from degrees to radians. Well, we're going to multiply. We're going to multiply by pi over 180 degrees, which is equal to 1. Right? It's kind of like converting feet to inches. You multiply by 12 inches per 1 foot, which is equal to 1. It's the same kind of idea. We're multiplying by 1 here. It's just pi over 180 degrees. So for example, if I want to convert, say, 30 degrees to radians, I'm going to multiply that. I'm going to multiply that by pi over 180 degrees. Now, a lot of people are just going to say, okay, well, this is going to be, so you don't have to show quite all these steps. You should show some steps when you're converting from radians to degrees to radians. I'm probably going to show too many steps here just so you can see everything. Some people might say, oh, that's 30 over 1, just to make it easier to do the fraction multiplication. And then when you multiply fractions, it's top times top, bottom times bottom. So notice I'm going to write 30 pi over 180. And in that step, I already canceled out the degree symbols. Right? That degree symbol there and that degree symbol there are going to cancel out and go away. And then I'm going to also reduce this fraction. That's going to be 3 pi over 18. And that reduces further to pi over 6. So 30 degrees is the same as pi over 6 radians. They're exactly the same. They're just different names for the same things. And we can keep doing this. We can take 90 degrees. We can multiply that by pi over 180 degrees. And then when you multiply a number by a fraction, that number just goes in the numerator. That's going to be 90 pi over 180. And that's going to reduce to pi over 2. Or 15 degrees, we can also convert, right? So you can convert any degree to radians. Sometimes it's nicer than others. So this converts to what, 15 pi over 180. We can divide top and bottom by 3 and get 5 pi over 60. And 5 goes into 60 12 times. So that's going to be pi over 12. One here. Sometimes people will ask you to get a decimal approximation, but not usually. So these are all the way I would typically write the answer. But you could also say, for example, pi over 2, if I was to convert that to a decimal, it's approximately 1.6. This answer is the answer we generally want. This answer is an approximation. But usually people will ask for an exact answer. So let's keep going here. Let me keep track of where my notes are going. All right, some things in the picture here. Sure, let's look at 1 or 2 more examples and then we'll go the other way. Let's see, sorry. Let's look at 225 degrees. So again, if I want to convert this to radians, I'm just going to multiply by pi over 180 degrees. And then, so we can do more steps at once, but the first step is always, I think, just to write it as one fraction. And then you can start essentially canceling out common factors. What's a good common factor here? I don't even know. So here's what I would probably actually do to make it easier. I might multiply this by 2 over 2. And then get 450 pi over 360. Because then it's easier to cancel a 10. So that's going to be 45 pi over 36. And then it's easier to see that 45 and 36 are both multiples of 9. So 45 is 5 times 9, and 36 is 4 times 9. You don't have to do it the same way I do it. You just have to be able to get to the same place. So if you see a different thing, like maybe you already see both the top and bottom here are divisible by 5 or are divisible by 9, that's also perfectly fine. Whatever you want to do. Let's look at one more. So let's say I wanted to convert 110 degrees to radians and also get a decimal approximation. So I'm going to multiply that by pi over 180. Just reminding you, we're just multiplying by 1. Pi over 180 is 1. And then that's going to be 110 pi over 180, which is 11 pi over 18. But if I wanted a decimal approximation, I would get out the calculator, in fact, or my phone, and right, we would do this. We would make it go sideways, then we would do 11 pi. We would be careful. We would do 11 times pi, and then we would divide that by 18. And we would get approximately 1.92. I will say the phone calculators are not my favorite for trig functions when we get to trig functions because they kind of have to do things backwards or what feels backwards to me. let's go ahead and talk about the other way. So we can also convert from radians to degrees by multiplying by the reciprocal. Multiplying by, instead of pi over 180, 180 degrees divided by pi. If you're ever not sure what you want to multiply by to convert, the thing you want to end up with should be on the top. So if you're trying to convert 2 radians, oops, sorry, you want the radian measure on top, pi radians over 180 degrees. If you're trying to convert to degrees, you want the degree thing on top and the radian thing on the bottom. So for example, we could convert pi over 4 radians to degrees. And we're going to do that just by multiplying by 180 degrees divided by pi. A lot of the time, the pi's will just cancel. So that's 180 degrees divided by 4, which is 90 degrees divided by 2, which is 45 degrees. Or maybe we have something more interesting like 7 pi over 6. Yeah. So we're going to multiply that by 180 degrees over pi. Right, it does start to get kind of old. The pi's do cancel. Now, we could do 7 times 180 degrees and then divide by 6, but I think it's easier to do some division first. 180 divided by 6 is just 30. So this is really just 7 times 30 degrees, which is 210 degrees. Sometimes people are going to give you strange radian measures. Not usually, but just occasionally someone's going to throw something weird at you. And they're going to say, how much is 20 radians in degrees? And this is where things get kind of less nice. We're still going to multiply by 180 degrees over pi. And then we're going to get, let's see, 2 times 180 is 360. So 20 times 180 is 3,600 degrees divided by pi. And if they're asking for an exact answer, that's it. But if they're asking for an approximation, we do 3,600 divided by pi, and we get approximately 1,145.9 degrees. So do be aware, sometimes people will ask you for an exact answer. Sometimes people will ask you for an approximation. What time is it? Yeah. Let's do. So converting is not too terrible. I will say there are more examples of converting on the previous year's notes that are in Canvas. They're in the module A. If you want to see more examples of that, I would encourage you to look there. But I probably should move on to talking about what the trigonometric functions of an angle are. So we're going to start with a triangle. We're going to start with a right triangle. So here's one of my favorite right triangles. The side lengths are 8, 15, and 17. And those side lengths do satisfy the Pythagorean theorem. It's definitely true that 8 squared plus 15 squared is equal to 17 squared. So for a right triangle, we always have the Pythagorean theorem. And now we're going to look at one of the, what do we call them? One of the acute angles in the triangle. One of the angles that isn't the 90-degree angle. Let's look at this one. And we're going to call it theta, the Greek letter theta, which is kind of the most typical name for an angle. You can use any Greek letter or not, but usually people use Greek letters. So alpha, beta, gamma, theta are all typical choices. So I'm just going to say what these are, and then we'll talk more generally. So in this triangle, the way you find sine of theta is it's going to be 8/17. Or some people would say the opposite over the hypotenuse. Cosine of theta is going to be 15/17, or the adjacent over the hypotenuse. And tangent of theta is going to be 8/15, the opposite over the adjacent. And these are what I usually call the primary trig functions. There are three others, which are called the reciprocal trig functions. And we usually write them next to the reciprocal. Yeah, exactly like Sohcahtoa, which we're definitely going to write down in just a second. But yes, you're on the ball for sure. So these definitely comprise, in fact, let's go ahead and just write it right here. These definitely do make up Sohcahtoa. And then we're going to write their three reciprocals. So cosecant of theta, which is abbreviated as CSC, is the reciprocal of sine of theta. It's 17/8. Secant of theta is the reciprocal of cosine. It's 17/15. And cotangent of theta, it was the reciprocal of tangent. It's 15/8. But yeah, you're right. I want to say Estefania. Yeah, there is this mnemonic device called Sohcahtoa that we use to remember what sine, cosine, and tangent are. So here's what we have very generally. So in general, we have a triangle with a right angle. Now, I want to make sure it's really, really clear. The hypotenuse is always the hypotenuse. The hypotenuse is always the longest side, and it's opposite the 90-degree angle, or the pi/2 radian angle. Right, so that angle right there, and that's 90 degrees, which is pi/2 radians. There are two other acute angles, and what you call the opposite and the hypotenuse depend on which angle you're talking about. So for the angle in this corner, this side over here is the opposite side. And this side over here is the adjacent side. But I'm not going to label it. But if instead we were drawing the angle up here in this corner, from this corner, this side would be the opposite, and this side would be the adjacent. So the opposite and the adjacent definitely depend on what angle you're looking at. The adjacent is always the side that's next to it that isn't the hypotenuse, and the opposite is always the side that's not touching it. Okay, and then, yes, we exactly have Sohcahtoa, where sine of theta, and I really should point out sine, when you write sine or cosine or any trigonometric function, you do need to have an angle in there. It doesn't make any sense if you just write the trig function and there's no angle to take the trig function of. So just like it would make kind of no sense to write a square root without anything in it, we don't write a trig function without any angle to take the trig function of. So sine of theta is the opposite over the hypotenuse. Cosine of theta is the adjacent over the hypotenuse. And tangent of theta is the opposite over the adjacent. So this is a great way to remember those three. The other three, there is not a nice device for. It does not work out to say cho, sha, kao. No, that doesn't work so well. You guys are like, what is he saying? I was doing the same sort of thing for cosecant, secant, and cotangent. But so right, you could try saying cosecant of theta is hypotenuse over opposite. I never remember these. I don't actually really know that cosecant is hypotenuse over opposite. What I know is sine is opposite over hypotenuse, and that cosecant is the flip of that. That's what I really know. Secant of theta is the reciprocal of cosine, so it's going to be the hypotenuse over the adjacent. And cotangent of theta is the reciprocal of tangent. It's going to be the adjacent over the opposite. That's how we actually know these things usually. We definitely, so if someone asks you to write out the 6 trig functions, so that's a good question. We don't use the trig functions to find the angle. We use the trig functions. So the trig functions are kind of an end into themselves, right? We're not at this point really using them to find any one thing, except to just evaluate them for what they are. So what I should say is we are defining the trig functions. Sine is defined to be, in a right triangle, the value of the opposite side divided by the hypotenuse side. The cosine is defined to be the value that is the adjacent side divided by the hypotenuse side, and so on and so on. So these are how the 6 trigonometric functions are defined for a right triangle. And I would encourage all of you to get in the habit of writing them in this order. Sine, cosine, then tangent, because there's the nice mnemonic device, and then their reciprocals right next to them. It's going to make it easier to, oh, if I'm doing the reciprocal of sine over here, I can just look at sine to flip it over, get cosecant. And then I would also just encourage, and this is not required, but something I would encourage you, is I would encourage you to say the names fully. Sine, cosine, tangent, cosecant, secant, cotangent. A lot of people like to say sin or cos or tan, or I don't know how you would say that without saying cosecant. Sec, cot, no. The full names, people will understand you better if you say the full name for the trigonometric function. So I would really, really encourage you, say cosine, say tangent. Your teachers will like you better for it, is the real truth. I know my teachers definitely were like, what is this? So yes, I don't really care personally. That's a total lie. I definitely care. I can't lie. I told it. It doesn't drive me crazy, but I'm like, just say it. But if you say it a different way, I will still understand what you mean. This piece of paper is great. Interesting. Weird things got printed on those pieces of papers. Okay. So what we will often ask you to do is to find the 6 trigonometric functions of an angle. So here is a very well-known triangle. It's a 3, 4, 5 triangle. And yes, I've definitely drawn it not to scale, right? That looks like trash. The 3 side is longer than the 4 side. The reason I've done this is because sometimes people are going to draw triangles that look totally wrong, and we're not going to care. We're going to be like, I want you to find the 6 trigonometric functions of the angle theta. So find the 6 trig functions of the angle theta. Great, we know how to do this. We know that sine of theta is the opposite side over the hypotenuse side, and cosine of theta is the adjacent side over the hypotenuse side, and tangent of theta is the opposite side over the adjacent side. This is the adjacent, this is the opposite, this is the hypotenuse. And then the reciprocals, I always do these 3 first, and then if I have to do all 6, I'm going to do reciprocal. So the reciprocal of sine is cosecant. It's going to be the flip. The reciprocal of cosine is secant. It's going to be the flip. And the reciprocal of tangent is cotangent. So cotangent of theta is 3/4. That's how we're doing the problem like that. All right, let's do another one. So we want to find the 6 trig. I'm getting a little bit more abbreviated with my writing here because we end at 2:20. Well, shoot. Okay, so let's look at this one. Where'd you go? Sorry, there's no picture. So we're going to call this one alpha. we want to find the 6 trig functions of alpha. And notice we're missing a side. So before we can start finding the 6 trig, so we could find sine, right? We could totally find sine. Sine of alpha is the opposite over the hypotenuse, which is 3 over the square root of 13. And if we, we'll worry about that. But cosine, we need the adjacent side. So to find the adjacent side, we're going to have to use the Pythagorean theorem. So we're going to take that side. So what we're really saying is this side squared plus this side squared should equal the hypotenuse side squared. So question mark squared plus 3 squared should equal the square root of 13 squared. So that's going to be question mark squared plus 9 equals 13. Or question mark squared equals 13 minus 9, which is 4. So that means our question mark has to equal the square root of 4, which is 2. And we only care about the positive square root. It's not the negative square root.
About the paper just a little bit. So
oh, thank you. I'm so sorry. Yes.
Oh, no worries. No worries.
So this is going to be equal to 2.
Do we have to leave it as a question mark, or can it become?
You can use, I was using a question mark just because I was, but you can use X or Y or some other variable, whatever you want.
Okay, cool. Thank you.
So yeah, now we know that third side is 2. So now we can find cosine of alpha as the adjacent over the hypotenuse, tangent of alpha as the opposite over the adjacent, cosecant of alpha as the reciprocal of sine, square root of 13 over 3, secant of alpha as the reciprocal of cosine, which is root 13 over 2, and cotangent of alpha as the reciprocal of tangent, which is 2 over 3. Okay.
Is there a difference that it makes when you're using theta and alpha, or?
Nope, no difference at all. Good question, no difference at all. We could really, I'm just changing up the letters so you are aware that people like to use different Greek letters. But then we could ask, I'm not going to answer this question, but we could call this other angle here whatever Greek letter I want. I'm going to pick beta just for the heck of it. And then we could ask ourselves, oh, what are the 6 trig functions of beta? But as far as what letter we're calling the angle, no, it doesn't matter at all. People just use different things to change it up. Let me see. So I have a minute left, and I do want to say one more thing. So there's another example of this in the older notes. So I would definitely encourage everyone to look at the previous notes, but I want to say one thing about using a calculator for finding trig functions. So fun paper, okay. So here's what I want to say. When you're finding trig functions using a calculator, you have to be aware of what mode you're in. So if you're trying to find, like, say, sine of 45 degrees, well, depending on what's happening here, and I didn't bring the calculator I prefer, but if you happen to be using your phone because it's handy, if you're doing a trig function of sine of 45 degrees, you have to enter the angle first and then do sine of that. Now, the not great thing about this is it's going to give us an approximation most of the time. Which that seems, oh, so I made a mistake. What's the mistake I made? I'm in radians. So sine of 45 degrees did not approximate equal 0.8509. Sine of 45 radians is approximately 0.8509. Sine of 45 degrees is equal to, so I'm going to change the degree here. Start over. I'm going to put, and again, this is not how I usually use a calculator, right? Usually I'm writing sine and then parentheses 45. This always feels totally backwards to me, but we put the angle in first and then do sine. And there's the correct approximation. Sine of 45 degrees is approximately 0.707. And we'll see later, the sine of 45 degrees exactly is the square root of 2 divided by 2.
Can you go over how you did it in the calculator real quick for the
yes, definitely. So again, depending on the calculator you have, you might enter it differently. But definitely on your this is an iPhone. On the iPhone, if you use the calculator that's with it, you have to enter the angle first. So let's do another one. Let's say I want to find cosine of 60 degrees. I would do 60, and then I would do cosine of that. So cosine of 60 degrees is 1/2 or 0.5. Two things. Be careful. Sometimes there's going to be like, so if someone wrote, for example, find, tangent of 3, it feels like it should be degrees because that just feels like it would be degrees, but there's no degree symbol written there. So if someone says tangent of 3, it needs to be in radians. So I would do radians, I would write 3, and then I would do tangent of that. And I would get approximately negative 0.143. Excellent question. Nadalin, I apologize if I butcher your name. You can always feel free to correct me. Yes, to do any of the reciprocal trig functions, that is an excellent question. So if I wanted to do cotangent of, say, 3 radians, I would take my answer for tangent, and then at least using this calculator, I would do 1 over that. So yeah, using a calculator, cotangent of 3 radians is equal to the reciprocal of tangent of 3 radians, which is approximately negative 7.015. Another example, and then I should really stop talking, to find, let's see what we got here. Let's say I want to find, sure. Let's say I want to find cosecant of pi over 6 radians. Okay, so here's how we have to do this with the calculator. We're going to do first pi divided by 6. Then we're going to do sine of that. And then we're going to do the reciprocal of that.
Sorry, we can't see the.
Oh, sorry. No, that's totally my fault.
All good. There we go.
I forgot. So let me do that again. So if I want to do cosecant, so let me write it out first, actually. So I want to do cosecant of pi over 6. What I'm really doing is 1 over sine of pi over 6. Or if you prefer, sine of pi over 6 to the negative 1 power. I should point out, because I'm sure some of you have a calculator with inverse trig functions, this is not at all the same as sine inverse. So just be careful. This symbol means something totally different than the reciprocal of sine. I know it feels like it shouldn't, but it does. So yeah, but anyways, to do this on your calculator, you would do, see, can we see that? Yes, we can see that. Okay. So you would do first the angle, because it's a backwards calculator. So I thought it's like a Boolean calculator. It feels backwards to me because I never used a calculator like this when I was younger. So you would first do your angle, pi divided by 6. And I think you have to hit equals before you start doing the trig function of it. And then we're going to do sine of that because we don't have a cosecant button. And then we're going to do the reciprocal of that, which is this 1 over x button here. And we're going to get 2. So I've talked too long, which unfortunately is typical. I usually try not to go too long because I know you guys have other things you also have to be doing. That said, I would encourage everyone, if you want more examples, to look at the notes that I posted from last time. And again, let me do one thing. Sorry, I know I said I was going to wrap it up, but I'm trying to. New share. Yeah. Great. So you look back, excuse me, if you look back at the modules, if you look at the class A notes and examples I actually used in class from last time, you'll see a lot of the things we did today, but also some extra examples that we didn't get to. So if you're looking for more examples, there are more examples there. I would encourage you to look at them. And then the other thing I wanted to say is that I'm going to hang out here. So if you want to stick around and ask questions about either the math or the how the class works kind of stuff, you are really welcome to stick around and hang out. I have work to do anyway, so I'm going to be in here for a while. But if you want to stay and ask questions, you're really welcome to. But that also said, you are welcome to also go. Class is officially over at this point. Except class is over, but I should say there's a homework assignment due tomorrow. It's due at noon tomorrow. Please submit it via Gradescope. If you have trouble with Gradescope, either get in touch with me or send me your homework via email. That is perfectly fine. I prefer Gradescope, but I can also manage. So if anything,
I did a question about Gradescope.
Yes.
It's asking for like a course number and it's got to be like 6 digits. Where do we find that?
Good question. Let me do one thing here. It shouldn't require that, but.
And would it, maybe you're doing it wrong, but I'm doing it like the sign up version. Am I supposed to log in? Is it already
You
created?
should be able to log in, but let me see here.
Okay, because I wasn't sure if I had to create an account or if it was already created.
I think I need to update the roster. So great. So I'm resyncing the Canvas roster. I think that should allow you to do it, but let me also go ahead and
Yeah, I just got a notification.
yeah, cool. But so if anyone does have issues though, let me know. I know there's a way to. It said you can also do this thing with an entry code, but like they're not actually showing me what the entry code is. Anyway, but it sounds like that took care of the issue.
Yeah, that's what it looks like. I just got like a set your password link and yeah.
Okay.
Thank you.
You're very welcome. I think I always feel like I think that's all I have to say, but one more thing. No, I really think that's all I have to say for today. I'm going to stick around. If you have questions, you can ask them now. You can email me them later. Just don't hesitate, right? We're here to help you. Like my whole job is to teach this class this summer and have some office hours. So I'm very available. Please do reach out. And I see someone has raised their hand. Go ahead and ask your question.
I just have a quick question. I don't know if I'm remembering right from like my last class in math, but with the square root of 13, if it's under the fraction, do we have to like fix it?
That's a very excellent question. I was kind of letting that go, but so what I would say is you don't have to rationalize it, but certainly it is considered more simplified to rationalize square roots in the denominator. So I should start sharing the correct screen here. Apologies. There we go. So, right, if you wanted to say rationalize this, you would take 3 over the square root of 13 and multiply it by the square root of 13 over the square root of 13. And then that would be in the top 3 times root 13. And the denominator, square root of 13 times square root of 13 is 13. I would say for now, you don't have to worry about rationalizing things, but we probably will move towards rationalizing denominators in the future. So yes, that's an excellent question. It is something that typically people prefer, if not require.